Anyway, so let's go back to op-amps. So I think I spent a lot of time talking about op-amps in general. I think the motivation behind using op-amps and op-amps in general is something we spent a lot of time on. So the one thing that I want to just refresh your minds on is the equivalent circuit that we talked about, the equivalent representation of the op-amp as a box here with two terminals that are open circuited, right? And an output voltage terminal that depends on the open loop gain multiplied by this differential input. So the output voltage here is the open loop gain multiplied by this input voltage between these two terminals. And since these are open circuited, we will always find that the current into this box is zero. If you have an open circuit, then the current going into this box is zero, right? The value of this voltage is what we can play with, right? Depending on what we put on the two terminals, right? So that's, I think we mentioned this last time. I just want to refresh your minds about it. The fact that we have an open, that these terminals are open circuited leads to something called that the textbook calls the summing point constraint. What does the summing point constraint mean? If this is an open circuit, there's nothing connected here, and this is an open circuit, nothing connected here, then this current is zero, correct? If this current is zero, then the current going into this node is the same as the current flowing here, since this current is zero. This is what's called the summing point constraint. The other, or this is one aspect of the summing point constraint. The other aspect of the summing point constraint is anytime we have this negative feedback, what did we do? We had a positive voltage here, right? This positive voltage was connected to this terminal here. This caused a certain value for Vx. This value for Vx, when it was multiplied by the open loop gain, remember the output circuit of this representation looks like the output voltage looks like the open loop gain multiplied by this Vx value, right? Anytime, so if I have V input and I don't have this feedback, I will have a value for Vx, which means the output will be a very large value. If I add this feedback here and V output happens to be negative, what did I do? I took a negative number. If it happens to be negative, we will see how we calculate it. If it happens to be negative, and this happens to be a positive value, what did I do? I took a positive voltage and sort of decreased it by a negative number, right? And proper choice of these values of resistances will allow us to decrease it to a certain amount such that this Vx tends to zero. If this Vx tends to zero, what does this mean? It means that there is no voltage difference between these two nodes, which means that I can consider this as a short circuit. So hence this summing point constraint means that the differential input voltage and the input current of the op-amp are zero. There are two conditions that define this summing point constraint. That this differential input voltage becomes zero, and the input current here becomes zero, leading to the fact that this current is equal to this current. Does this make sense? So this is not really connected. It is an open circuit, but the voltage is zero. So I can still do Kirchhoff voltage law. If this is the voltage, and I want to find the input current, what does the current here look like? It's this voltage divided by this resistance, and this is a voltage, zero, plus Vx, so right? V output equals, this is the current, the voltage drop is in the opposite direction, right? So it's the voltage drop here, V input here, this voltage is equal to I1 times this R1 plus Vx, this Vx here between these two terminals. If this Vx is 0 because of negative feedback, right? In general, it's not. Initially, if I remove this feedback, it's not 0. It's 0. Right? If I remove this feedback, it's equal to V in. Vx is equal to V in because it's the difference between the voltage at these two terminals. If I provide some feedback that is in opposition to the input that I have coming in, I'm able to decrease that value of the voltage. So, in a controlled fashion. Ideally, I would like to make it such I choose the values of resistance such that this Vx is equal to 0. But remember, this is an open loop. This has an open loop gain of infinity. So even if a small piece of infinity will be able to oppose anything that I put in and drive this input to 0. That's the idea that we're doing here. That's what this ideal op-amp or summing point constraint means in some sense. Right? So if I drive this to 0, then it's an open circuit, but it has a voltage across it of 0. So I can do a Kirchhoff voltage law around this loop, and this equation will be correct. And this just will happen to be 0, which means that the input current is equal to V input time divided by R1 in this case. What does this current equal? This current here is equal to this current as well, because the fact that this current is equal to 0. So at this summing point, Kirchhoff current law at this node means that the current coming into this node is equal to whatever is coming out because this is 0. Right? So these two things happen when we have this negative feedback. Is everybody okay with that? Okay. So let's see how we calculate the input to output characteristics of such a circuit, such an op-amp circuit. So first we will study a class of amplifiers called inverting amplifiers, and we will the name inverting comes from the fact that their output voltage will be negative of the input, will be opposite in polarity versus the input voltage, not negative of the input voltage, opposite in polarity. The magnitude will be changed by the value of the resistance that we choose around it, but it will be opposite in polarity of V input. So if I put V input of 5 volts, the output will be minus something. This something will depend on the values of the resistors around it. Okay, so how do we calculate the output voltage versus the input voltage? So again, the quantity of interest is the gain, right? Like the filter circuits that we were talking about. I have a certain input and I want a certain output. That certain output, I want to attenuate it, or I want to make it larger, or I want to, I want to attenuate it or make it larger, and I want to do that maybe at different frequencies, right? So different circuits will do these things. I want to integrate it. I want to add the two inputs. I want to do many things, right? So with this specific circuit, what it does is applies a certain gain to the output, depending on the values of resistors, and flips the sign of the output versus the input. So how do we do the calculation? So how do we do the calculation? We have to depend on the summing point constraint that we talked about. The summing point constraint says what? It says that this Vx voltage is equal to 0. And it says that the current here is equal to 0, which means that the current in this branch and this branch are equal, right? So that's really what all of this says. And if we apply this and we see what we have here, so here we're going to calculate the input. So we want to calculate V output over V input. This is our goal. AV is V output over V input. So we want to find the relationships that sort of tie these two together. So let's do this. So what is the input current equal to? This input current, I1 or I input, is equal to I input or I1 as they call it, is equal to what? V in over R1. This is R1. Right? Remember, I can do Kirchhoff voltage law around this loop. This voltage plus this voltage plus this voltage are equal to 0. Right? So this, and since this is 0, then these two are equal to each other and opposite in polarity. So sorry, this one minus this one is equal to 0, which means that V input is I1 is equal to V input over R1. How about I2 is equal to I1, which is equal to V input over R1. How about V output? Same. This is a voltage, and there's current here, so there's a voltage drop. Remember, current and voltage drop are opposite polarities. So current flows from the positive to the negative voltage potential, right? So V output plus this voltage, and this is 0. This is one loop here, right? I can use this loop here, right? This is one loop, so V output plus this voltage plus 0 is equal to 0, right? Or minus voltage is also 0 is equal to 0. What does this mean? It means that V output is equal to minus this voltage. This voltage is what? Is I2 times R2. I2 times R2. I2 is equal to V input over R1. So I'm left with the output is equal to minus V input over R1 times R2. Sorry, where the times R2? This is not multiply. It's not minus R2. Sorry. Right, it's I2 is equal to V input over R1. So V input over R1 multiplied by R2. So I just rewrite this as minus R2 over R1 times V input. So V output over V input, V output over V input is equal to what? Minus R2 over R1. Okay? So this is the gain of the amplifier. So anytime you have an input signal, it will be multiplied by this number and then inverted in sign, and that will be the output. Right? That's why it's called an inverting amplifier. Yes? Question? Yes, yes. Is it not clear? Should I repeat? Summing point constraint? Yeah, this is 0. I here is equal to 0. This? Here? You can, but so if you did KCL, so this current here is V input over R1, right? Which means that this current is also V input over R1, right? But here, do you know what's coming out of here? No, that's not 0. No, that's not 0. Why would it be 0? The equivalent circuit, remember the equivalent circuit for this box looks like this. 2 terminals open circuited, and then 1 terminal with a dependent source here. So there's a dependent source. You actually, what you did was this. Why would this current be 0? Right? There is no need for this current to be 0. So are you okay with this? So let's see. This is what they did on the next slide. So they just did what we did was, Z input is equal to. So I just defined some stuff. So V input divided by R was the I input, right? Or the R input or R1 is V input over I1. This is also called the input impedance of the amplifier. right? Do you want the input impedance of the amplifier to be big or small? Remember, the ideal op-amp has an infinite input impedance. Why is that very nice? Because it doesn't require any current to be consumed from my sensor. So I still want an op-amp circuit to have a high input impedance. An amplifier circuit, this is an amplifier. It will take your signal and multiply it by minus R2 over R1. Right? It will take your V input, your sensor data will come at microvolts. And what this amplifier circuit will do is take this input voltage, multiply by minus R2 over R1, and this will be your output. Do you want to consume high current from your sensor? No, you don't. So do we expect that this signal, this circuit, will have an input impedance to the current from your sensor? Yes. I mean, this is the sensor. This is your sensor in this case. This is the current coming in from your sensor. What is the impedance that it is seeing? It is seeing an impedance equal to V input over I1 over the current that's flowing. Right? V input is your sensor voltage divided by the sensor current. That's the input impedance that the sensor is seeing. As if there's a black box, like there's a Thevenin equivalent circuit with just an impedance. What is that impedance equal to? Equal to the voltage divided by the current. Right? You want that impedance to be high so that the current is small. You don't want high current to be consumed from your sensor. So that's typically amplifiers will have a large input impedance. Right? How about output impedance? Let's think of what we mean by output impedance. You have a circuit. You have a circuit here in a box. It just happens to be a power supply and a resistance. And then this is your load. These are your terminals outside this box. These terminals have a certain voltage, the output, and a certain current. Right? If this current increases, right? If this current increases, if this current I increases, what is going to happen to your output voltage? If this current increases, your output voltage, let's say this is limited to V. Right? This is a voltage source with a value of V. Right? The output voltage here is equal to what? Is equal to what? Is equal to V. This is the current flowing. This is the voltage drop in the opposite direction. It's equal to V minus, this voltage drop, I'll call this V1. Right? So output voltage is equal to V minus V1. V1 is equal to what? I, the current multiplied by this resistance. Right? So now what's going to happen if the current increases? Huh? Yeah, exactly. The output voltage will decrease. So the more you increase the current, the output voltage will actually decrease because of what is called an output resistance of the circuit that's feeding your load. Right? So if your circuit does not have an output resistance, like if the output resistance is zero, then you increase the current, nothing will happen. You will still get the same voltage at the output. Right? If your circuit has an output resistance or has an output impedance in the general case, if you're feeding into the AC output, if you're creating an AC output, then what that will do is will decrease your output voltage going to the circuit. Right? So output impedance is not a good thing. Do we agree? Now let's go back to the op-amp, ideal op-amp circuit. What does the ideal op-amp circuit look like? Yes, ma'am. Okay. Okay, let's the ideal op-amp circuit looks like this, right? This is my V output, and this is the open loop gain times Vx, and this is Vx. Do we agree? Great. So if I try to pull more current from this circuit to feed my load, for example, is my output voltage going to change? The output, what is the output voltage equal to? equal to the open loop gain multiplied by Vx. Right? This is what V output equals to as we know it. If I pull more current, if my load, my circuit is consuming more current, what is going to be my output voltage? In this case, is it going to decrease? Okay, this case, let's versus this case. How about this case? This is another case. This is your same load now, and this is your output voltage. This is AOL times Vx still, okay? This is some resistance R. Now, what is output voltage in this case? Output voltage in this case is AOL times Vx minus I times R. Here, it's AOL times Vx, right? There's no output impedance as such. Right? Output impedance is basically a series voltage drop in the path of the current produced by your source. Right? That's what it is. It's something that's not your circuit, it's not your load. It's inherent to the source that is supplying this power. Like a battery, chemists make batteries for electrical engineers, right? Every battery has an internal impedance. The way we model a battery is an ideal voltage source. The way electrical engineers model a battery is an ideal voltage source with a series resistance. This is how we model a battery. Because we know that the more current we draw out of this battery, the more voltage drop I will have here. So the output voltage of the battery is equal to the ideal voltage source minus the voltage drop across this resistor due to the current flowing. Right? So this is called in battery. Have you studied batteries at all? So I'm sure you've heard of internal resistance. Okay, so output impedance is like internal resistance. Does it make sense now? Okay, that's good. It's good that you studied batteries. Who teaches the batteries? Where did you say? Which course? Basic physics. Okay, good. So anyway, so output impedance is like the internal resistance of a battery. Alright? So ideally you want that to be 0. Right? And input impedance, I want it to be high. Right? Because I don't want current, coming in from my sensor to be high at all. I want to be as low as possible. I just want to measure the voltage basically. I want to take that and amplify it. And I want at the output to consume as much current without changing the level of voltage that I have at the output. Right? So that's why input impedance high, output impedance ideally 0. Okay. So here we just define certain things like input impedance and output impedance. So output impedance is 0. Right? So everybody's okay with this now? Okay. So let's do an example. This what this example does is we add two signals VA and VAB. How do we do that? Can somebody help me analyze it? We really need to finish this chapter today, so because I'm really slow. So how do you analyze? How do you go about analyzing this? Same process. Remember, first we look at the circuit and make sure that there is feedback. There is feedback from the output that is going to cause Vx here to equal 0. Right? Because so we will only analyze circuits with Vx equal to 0. Right? So that's really what we're going to be doing. Otherwise, it's going to be a comparator like we did before. The output will be basically saturate to the open loop gain. Right? It's going to be the open loop gain multiplied by the input voltage, which is a large number. Right? So anytime you have this feedback, then what that is doing is driving Vx to 0. And we know that ideal op-amp, I here is equal to 0. All of these things we know. What does this tell us? It tells us that this current here is equal to this current here. Great, all this stuff we know. Right? So now, what is this current here? This current here is the sum of this current and this current. So this current is IA and this current is IB. So what is IA equal to? VA over RA. What is IB equal to? VB over RB. So this current I X here is equal to IA plus IB. IX is also equal to this IY, right? So IX here is equal to IY. What is V output? Remember, we want to know what the output voltage is. Always, that's what we want to do. What is V output? V output is equal to what? This is V output. Is equal to IY multiplied by RF, right? IY multiplied by RF, right? This is current here and voltage here. So minus, sorry, right? Because this voltage plus the voltage across the resistor is equal to 0 because of this condition here, right? So V output is equal to minus IY times RF, and IY is equal to IX. So let's put minus RF outside here. IY is equal to IX, IX is equal to IA plus IB, so this is equal to VA over RA plus VB over RB. So, right, this is the final answer. Alright, I can rewrite, the way they rewrite it is minus VA RF over RA minus VB RF over RB. Not clear? Oh, sorry. Right? I just redistributed, but the idea is I took my input voltage, multiplied it by a gain, and my other input voltage, I multiplied it by a gain, right? So basically, if I take this minus sign outside and I have a negative sign outside, and I'm adding the two input voltages multiplied by a gain, I can make this gain equal to 1 if I want to, right? In that case, I'm adding the inputs alone. I'm adding the inputs, but I'm flipping the sign, so you just have to make sure. So everybody's okay with this? So use the ideal op-amp assumption to solve the output voltage in terms of the input voltage and resistor values. That's what we did here. What is the input resistance seen by VA? What is the input resistance? So VA, input resistance seen by VA is equal to what? Remember, V equals IR. So the input resistance seen by VA source is equal to VA over IA. And input resistance seen by VB is VB over IB, right? So what's this and that? What is the output resistance seen by RL? What is the output resistance seen by RL? So let's look at the output voltage. The output voltage, remember the output voltage in the case of the ideal op-amp was equal to what? The open loop gain multiplied by Vx, the input voltage. Did this depend at all on any of the on any resistances? There is no dependence on the resistance at all, right? So since there is no dependence on the resistances, we said that the output impedance of this circuit is equal to 0, right? There is no output impedance to this circuit. But when we added an impedance in the path here, what was V output equal to? V output was equal to the AOL times Vx minus I times R, right? This R that was in this R here, right? In this case, the output impedance was equal to R, right? It had a value. Let's look at the equation for output voltage. If the output voltage equation here output voltage equation does not depend on, no, actually, let's look at, let's rewrite this one again, sorry. AOL times Vx, and this is R, and this is RL. The output voltage equation here, if I change the value of current flowing in the output, right? If I change the value of current flowing in the output, what will happen? Is there anything in the path of that current? Remember, there's an open loop gain here, and the circuit looks like this. This is AOL times Vx. This source is AOL times Vx, and I have a node here, right? If I change the load current here, if I change the value of current here, is this output voltage going to be affected? It will not be affected. It will never be affected because I have a voltage AOL times Vx here. Right? This output voltage here will not be affected at all. Right? So the output impedance is equal of, what is the output impedance resistance seen by RL? So how do you calculate that? If this was your circuit, if this was my circuit RL here and an R here, and this was my output voltage, the output, and this was my current, I. What is the output over I equal to? What is the output over I? Remember your short circuit current? V output over I is like what? It's like putting a short circuit here and calculating any resistance in the path. Right? So V output over I, if I have a resistance here, would be equal to this resistance. How about if I have no resistance? If I have a source here, no resistance, and this is V output, and I put a short circuit here. V output over I, in this case, will equal to what? 0. I don't know if it's clear or not. Yes. If I want to find the Thevenin equivalent resistance seen by the output, how would I do it? Like, this is my Thevenin, this is my op-amp output, this is my circuit. I will redraw it in terms of the ideal op-amp. So I have a source here, and this is my feedback resistance, and this is my output circuit. This AOL times Vx. This AOL times Vx. Vx is equal to what? Since I have feedback, Vx is equal to 0. So this dependent source is equal to 0. So my output circuit looks like something like this, right? Something hanging up here, right? That is not connected to the output at all. And this is my V output. And this is my current here. Right? So I would like to know what is the Thevenin equivalent resistance seen by the load. So what did you do? You looked at whatever is inside this circuit. If it's a voltage source, you put a short circuit. If it's an open current source, you put an open circuit, and then you calculated the resistance. Here, if you look through here, what do you see? R equal to, you see what? You see a short circuit, and you see nothing but a short circuit. What is the equivalent resistance, Thevenin resistance for this block? This is my circuit. 0. R Thevenin is equal to 0. That is the output resistance seen by the load. How about if I do this? put this dependent source and have a resistance here, and this is your output. This is RL and this is R. Again, what is the output resistance seen by your load? What do you do? This dependent source has a value that's equal to 0 because of Vx equal to 0. So this is a short circuit. And you're left with a circuit that looks like this. This is your circuit. And these are your two terminals for your Thevenin equivalent circuit. What is the equivalent resistance seen by these two terminals? This resistance R. Right? So your Thevenin equivalent resistance seen by your load is this R value. The output impedance would be R in this case. In the previous case, the output impedance is 0. I don't know, is it clear or not clear? Not clear? Forget about op-amps. Just forget about op-amps, right? Just think of Thevenin. You have a Thevenin equivalent circuit that looks like this. So you have a circuit that looks like this, and you want to find the Thevenin equivalent impedance. And you have another circuit that looks like this, and you want to find R Thevenin. R Thevenin in this case is 0. R Thevenin in this case is R. Okay? And V Thevenin is 0. Here V Thevenin is also 0. Right? Because Vx is 0 also. Right? That's why I put this short circuit as 0. But what's important is the idea of the output impedance of this resistance RL. But in the textbook they don't explain it as well. They just say, yeah. So I don't have the answer here, but the answer is what I gave you. Basically, what we went through is the answer. It's and the solution is in the textbook. Yeah, the gain is what we discussed. Yeah. Now we discussed the inverting amplifier. How about the non-inverting amplifier? What do you think the non-inverting amplifier would do? The output voltage will have the same polarity as the input. That's the only difference between them. But we still have the same concept. The idea is, again, if I don't have this R2, look at the circuit initially without this R2. If you don't have R2, what is V output equal to? What is V output equal to without R2? Come on, guys. Come on. The open loop gain multiplied by VI, this VI. And this VI in this case is equal to V input minus 0. Right? So the output voltage is a positive number. Before, what did we have? We had, if you looked at before we were connecting the source to the negative terminal. Before we had V input here, and this was connected to ground. What was V output in this case? It was negative the open loop gain times VI. Okay? So, no, it was the open loop gain times VI. But what was VI? VI was, remember, it's the positive minus the negative. It's 0 minus V input. That's where this V output is minus AOL times V input comes from. Right? So this is, what is this called? This is called inverting amplifier configuration. This one is called non-inverting, right? Because of the fact that we have a positive value here. Okay? So now I will go and put this. So remember, without R2, the output was the open loop gain multiplied by V input. It's a big positive number, right? I took this big positive number and I fed it back So instead of, originally I had AOL times VI, where VI is V input, minus 0, which is AOL times V input. But if I feed back a positive number, instead of this 0, I put back a positive number. What will this do to everything in parentheses? Huh? I have AOL now. This is what, guys, before R2, my output voltage was equal to AOL times V input times minus AOL times 0, right? Now it's going to be what? If I feed back something instead of the 0, right? This will have a value, and this will have a value, and they're both infinite. So what does this mean for Vx, or V output, sorry? Yeah, the open loop voltage, if it's an open loop, right? But it's no longer open loop. In this case, if I feed back this voltage, it's gonna be driving this to 0. This is VI, right? I drove this to 0. If I feed back a large positive number, and that's what I did. I connected it in non-inverting amplifier mode, which results in a positive output voltage here. I took part of this positive voltage, I connected a resistor to this positive voltage. At the other terminal of the resistor, I have a positive voltage as well, right? Less, more, doesn't matter. It's a positive voltage. Since it's connected to a positive voltage, it will be a positive voltage. So this is a positive voltage. What did this do? This drove VI to 0. What does this mean? It means that the negative feedback exists. If my negative feedback exists, then I'm happy I can do the same sort of analysis that I did before. I have this I equals 0, this I equals 0, and if this I is equal to 0, then the current here and the current here are the same. Correct? We're okay with that? And I can also use this loop here, this voltage here, plus this voltage here is equal to this voltage plus this voltage. This is a loop, right? And this is 0. I know that this is 0. So this voltage is equal to this voltage V1 in this case. We're okay with that? And I can also use the output voltage here is equal to what? What is the output voltage equal to? Output voltage is equal to, right? I have this voltage and this voltage. Output voltage is equal to V1 plus the voltage across R2. So I can do some things. I can manipulate the circuit and play around and see what we can do. Because the ultimate is I would like to see what the gain of the circuit looks like, right? That's my objective. I would like to see what the gain of from input to output looks like for this circuit here. So let's see what we have. But first we have to make sure that negative feedback exists, so that this VI is equal to 0. Right? As soon as I brought this feedback back, this VI is equal to 0. This VI is equal to 0, it means that the input currents to the op-amp are equal to 0. And that this current and this current are the same. All of this is a result of the feedback that I've created. So we said, okay, so let's calculate the gain. Do we calculate the gain in the next slide? No, it's not calculating the next slide. So let's calculate the gain for this non-inverting amplifier. We have a minute, I understand. So we have an amplifier circuit here. This is positive, this is negative. This is my output, RL, this is the output, and this is the input, plus minus, and this is R1, and this is R2. What did we say about VI? VI, as soon as I have the right feedback, right, then I drove VI to 0. Vi is equal to 0, that means the input currents here are equal to 0. These I inputs are equal to 0. So, and I will call the voltage across this resistor V1. So, what is V input equal to? Let's do Kirchhoff voltage law around this loop. This voltage plus this voltage plus this voltage. There's a loop here, right? So the sum of V1 plus V input is equal to, the sum of V1 plus Vi is equal to V input. So V input, since Vi is 0, then V input is equal to V1. And what is V1 equal to in terms of V output? This is V output across RL. This is a loop. No, they're not equal. I have V output across at this node, and this is ground. I have V output across these two resistors. Right? So I use voltage divider rule. So what is V1 equal to? Equal to V1, V output, multiplied by R1 over R1 plus R2. Right? So, and this V1 is equal to V input. So I have a relationship between V output and V input equal to R1 plus R2 over R1, which is 1 plus R2 over R1. This is my gain. This is the gain of this circuit. Does this gain of this circuit, does the voltage of your output change due to any characteristics of the op-amp? Remember, this op-amp circuit looks like, and there's a open loop gain here, AOL times VI. This AOL times VI is 0, right? This AOL times VI is 0, right? There's nothing here. So the voltage is defined, the voltage at the output is defined really by the external circuit. It has nothing to do with the load resistance changing. What does this mean for the output impedance? Output impedance is also 0. So we calculated the gain, we know the output impedance. We'll stop here. Next time I was hoping to wrap up this chapter today, but not possible. I don't know if is it confusing or, so can you